All right. Our remember that our conditions. We talked about these yesterday. Our conditions are linear, but not quite. Right. And the main new ones here that you're looking at is are they linear, which we're going to look at scatter plot and residual plot, and is there equal variance? So easy way to see that is, are the residuals like equally spread out as I go from left to right along the line? Okay. All right, here comes some formula stuff that you're not going to need to know. So we're going to do it quickly. There are a couple things that are important. I'll stop and point them out when they come up. But we did this example yesterday. Okay. So I'm going to go pretty quickly. Inference about the regression model. Oh, alpha plus beta x. The reason that we're using alpha and beta here is because these are parameters for the actual slope and y-intercept of all of the data. And then we use a and b for the slope and y-intercept of the regression line that we actually get from the sample. Right? Keeping with the pattern of Greek letters for the parameters, and then our usual alphabet letters for the statistics that we get from the sample. So when you see beta, that's the slope for the population. When you see B, that's the slope for our sample. All right, going on in fast forward here. Calculate main parameter. S is standard deviation of the residuals. So it is how far, on average, the residuals are from the line. So there'll be some problems where that's something we learned in chapter 3, that S is standard deviation of the residuals. So I just want to remind you of that going forward here. All right, and then we have this example that we did. I just want to remind you, this is what the equation would look like. This is a constant, so that's the y-intercept. This is attached to the variable, so it's the slope. We know how to interpret these. The slope would be as x goes up by 1, y is predicted to go up by this amount. Remember to use predicted for y on these. Remember to put a hat above y on the equation. Y-intercept is when x is 0, y is predicted to be this. S is standard deviation of the residuals. Moving on. That's all things that we did in chapter 3. And we've been reviewing a little bit, so that should look somewhat familiar to you on some of the scatter plot questions you've gotten on some of the FRQs. All right, whole bunch of samples. The shape is going to be normal. The mean is going to be at the mean. Standard deviation is some formula. All right. Oh. Degrees of freedom is different this time. N minus 2 instead of our usual N minus 1. Out of all this formula stuff, that's probably the most important thing. The degrees of freedom has changed. Put a box around it, highlight it, whatever. N minus 2 is our new degrees of freedom. And we're going to use t-scores when we do this. You're going to see t-scores when we do this. N minus 2 is our degrees of freedom. All right, back into fast forward. Let's see, degrees of freedom. So if the sample is 20, 20 minus 2, 18 for our degrees of freedom. All right. Our good old confidence interval formula. So t-score times standard error. Standard error is some formula that you're not going to have to calculate. So we're not going to really talk about it. Okay, where are we? All right. The reason we're not going to have to calculate is either you're going to put all the data in the calculator. That's possibility number 1. Or possibility number 2 is that you will have a table like this, and in that case, you'll be able to get the standard error from this table. Notice how one of the columns here is standard error coefficient. And so the standard error coefficient is here for my slope. Okay, we're going to be doing this. This confidence interval to get an estimate for the slope of the regression line. So confidence interval for the slope. And so standard error for the slope, we go to my slope row, which is the one with a variable attached to it, go to standard error, that's what goes in the formula. The t-score, we do the same way we have gotten the t-scores for confidence intervals. The sample size was 70, so degrees of freedom is n minus 2. So we get our inverse t for that confidence interval. That would be inverse t of 0.975. Oops. Wish I'd done that 2 at a time. So 68 would be our degrees of freedom, n minus 2. And then the confidence interval is our point estimate for the slope, which is up here, plus or minus our t-score, times the standard error, which it just tells us is the 0.002018. So this becomes our formula. Nothing fancy with our, nothing fancy with the formulas that you will need to calculate yourself. Just get the values off of the table. And then we are 95% confident that the actual slope of the population regression line falls between these two values. Question?
I put in inverse t in the calculator, and it gave me like a 4.1 something for the t-score. So, second distribution, inverse t. Paste.
Oh, that's because you put it in twice. When you did it here. See how it's in there twice?
Oh.
So you're taking this times this, and then it's telling you that that's 4.
Oh, okay.
That's what happened. Another case where I walk over there and it's fixed. All right, any questions on that? Okay. So next we're actually going to do a 4-step problem here. So for those of you that are ready, take a look at that next example and put that data into lists 1 and 2. Because now we're going to talk some calculator stuff.
Is this the fidgeting keys one?
Yes. Yes. Take data, put in list 1 and 2. We're going to do our 4-step process for a 90% confidence interval here. It's got the table, but we're also going to put the data into list 1.
So when we
I would say talk about the flight time regression line between these two variables so that you have some context to the problem. So that you're not just saying the slope.
I'm okay.
We all ready? Okay. So again, here's our data that we're putting into list 1. Lists 1 and 2. So the NAA change goes into list 1. The fat gain goes into list 2. Okay. So just a reminder of how to get the line. Stat. Over to calculate. I go down to A plus BX. That's the general format of it. X list 1. Y in list 2.
How did you know mine was list 2?
Store regression equation. This is the option that you want. This is the important one. You want to tell it to put it into Y1 so that it automatically puts the line on the graph. There's other ways you can do it, but this is the easiest way. Into Y1. So to bring up Y1, you can go alpha trace, or you can go vars over to Y vars function Y1. So the other way you can do it is with you hit alpha and then you hit trace. Some calculators don't do that. Some calculators don't have the alpha menus. So the other way is with vars over to Y vars function Y1. And then calculate. It'll tell you what the equation is. If you go into Y1, there's R and R squared. You should remember what those mean. And if I go over into Y1, there's the equation. If I go zoom 9, there's the line.
Oh, I missed that whole thing. I was writing down the steps. Yay! Okay. Calculate.
I did it myself.
We ready?
No, wait, what are we doing next? Okay, so I did the Y1 is the line reg thing, right? And then
Yes.
I clicked calculate.
Yes.
And then from there, zoom 9.
Zoom 9. And the line should be there.
How do I get out?
There's the line. Okay. So we have our scatter plot, we have our line. Good? Okay. Now we need, and by the way, notice that the equation, the y-intercept and the slope, match the y-intercept and the slope that are sitting on there on the table. Right? These decimals should match what you should get here. Okay? All right. Let me write out the conditions, and then we'll go back to the calculator. We're estimating the true slope of the regression line between these two, 90% confidence level. Linear but not. Here we go. Linear, does it look like a line? That line's a pretty good fit for the data? Yeah, it does. All right. Independent. 10 times sample size. It's going to keep going. Normal, there's the histogram. That looks pretty symmetric. We're probably good to go. Equal variance. Is it spread out about the same as I move from left to right throughout the data? Well, maybe except for this one point up here. Aside from that, we look to be pretty good to go. That the variance of these looks about the same. The residual plot is what you want to look at. That's why we're coming back to the calculator, because we'll need to make the residual plot. And then they were randomly selected. We took a random sample of 16. Okay. So those are our conditions. So again, let me explain equal variance one more time. Equal variance means the amount that the points vary from the line of best fit. That's what residual is measuring. It's observed minus predicted. So to get our residual plot, I look at it and say, is the amount that we are varying about equally spread out as I move from left to right? So here's how far apart I am at the far left. Here's how far apart I am about at the middle. Here's how far apart and spread out they are at the end. And it looks to be about pretty consistent and even throughout. That's what I'm looking for. Again, if the equal variance were violated, it would look something like this. It's very narrowly spread out, and then as I move to the right, it starts to get more spread out. This would be violating the equal variance condition because the variance is changing as I move along my line. Okay?
Yes.
All right. Any other questions on those conditions? Okay, back to the calculator. Again, pretend all those points erased. All right. What is a residual? I said it a minute ago. What is residual measuring? When I made the residual plot, what were all those points on the residual plot? How far what is from what? It is, residual is measuring basically how far off are the points that we get from what the regression line says. In other words, the formula for getting my residuals, if I can spell it right, observed minus predicted. Which is what you said, and then you were like, oh, never mind, I'm very wrong, ignore me.
I do that in chemistry all the time. I'll say something. It's like comprehending it, but we just think we're wrong. And so we're like, oh, never mind. Or you know what else they do? Someone else will say an answer and it's wrong, and I'll say the right answer.
So we need to get, okay,
It's the best when you get it right as a kid and says the wrong answer. And then you're
back, we're back. We need to get these values and figure out how to get these values out of the calculator. Observed minus predicted. So let's go onto our lists. Now, if you want to write down the steps, you can. But what I'll say is that you probably wrote down the steps in chapter 3. Do you remember them? No. So keep that in mind if you're like wanting to just memorize a whole bunch of steps. That like a month from now, are you going to remember them? What I do want you to remember is observed minus predicted. And if you can remember that, then you can logic yourself into what to do on the calculator. So here's my list. Where are my observed values? It's in L2. It's my observed values. My observed values are the observed y coordinates. So they are sitting right now in list 2. So I have observed. How do I get predicted? What are the predicted y values? I'm not talking in the calculator. I'm talking in general. The predicted values
I thought the fat thing was the Y.
the predicted values are y hat.
Oh, we're doing predicted, not expected.
Yes.
That's why it's
Yes. Predicted values are y hat. So it is what I would predict, what the line of best fit, what the regression line predicts, I get out for y when I put that value in for x. So what I want to do to get the predicted is take each of these values and put them into the equation.
No, he has a shortcut.
That's my predicted.
But I thought
So you can either do that one by one for all 16 values, or you can make the calculator do that for you. Let's go to list 3. This is where we're going to put our predicted values. So the predicted values, here are my x values. They're in list 1. I want to take them and put them into the equation. Where's the equation right now in the calculator? In y1. So I'm going to go, you can go vars over to y vars, or you can go, this time I'll show it as alpha trace. y1. And what do I want to plug in?
L1.
L1. All the x values, which are in list 1.
I don't know how to get L1.
Second and 1. Okay? So this is what goes in list 3. It is saying take all the x values, which are in list 1, and put them in the equation, which is in y1. Hit enter. There they are.
I got an error. Yeah. Wait, I want to get an error.
Let me come back to you. Let me show the rest of this. So here, my observed are in list 2. Here are my predicted in list 3. So if I want observed minus predicted, let's go over to list 4 and put in observed minus predicted. Observed minus predicted. There are your residuals.
Wait, L1 minus L2?
Nope.
Oh, 3.
Remember, list 1 is all your x values. So that's not observed or predicted. The observed are in list 2, the predicted are in list 3. So that's your observed minus predicted.
Is the residual in list 4 then?
The residuals are in list 4. Okay. Any questions on the lists? We cleared up our errors?
Oh, mine are different than yours. Oh, no. That's okay. I'm scared. Mine are too. Dang it. What did I do wrong? Yeah. I have an error. Wait, Matt, did you both or for list 4? Does it start with
Make sure you're putting it in up.
782?
Hold on. Yeah, up the top. Yep. Yep.
Oh, dang it. Frick. What did you do? List 3. No, list 1.
List 2.
Ah. List 3 or 2. List 3. Okay, good job. Maybe you said it wrong.
Again,
I typed the right thing in though.
these are, watch up here so that you know, so that you realize why you're using list 2. These are my x values. These are where my x values are. These are my y values, which are my observed. So here's where the observed is. These are my predicted. This is where I did take all the x values and put them into y1. So here's my observed, here's my predicted. We're going to subtract them to get the residuals. Observed minus predicted. Observed is in list 2, predicted is in list 3. One more step. This part is actually making the graph. So go into your same place you made the scatter plot before. The x values are still the x values. For the y values, we want the residuals. And where are the residuals? They're in list 4. Stat plot, same place you made the scatter plot. So instead of list 1 versus list 2, which is where the y values are, now we're going to do list 1 versus list 4. And we're going to go zoom 9. There's the residual plot.
Which one's the residual one?
The residuals are what we ended up with in list 4.
Oh, but it's not. Oh, it's the same thing. It's the same thing.
All right. Questions on that?
So we just needed the residual plot.
These should take longer, right? Because I can already see this.
Like 30 minutes for a talk.
No, this is what I think.
We just needed the residual plot.
It depends on what you have.
Okay, so we only did all this work just to find out
The residual plot for the conditions.
condition. Yeah.
Yes.
This is all.
Yes.
That's all just for one step of the process. Can I just say
All right.
all the conditions are good and then
Yeah.
be like, ooh? Because they're
All
not
right.
gonna like have you trace.
Questions up to this point?
They can't see my calculator.
There will be cases where like one of them is not like remember the first example like it wasn't met for a reason. That's
Let me finish.
Just give me like your estimate.
Let me finish. Step 3.
We're not done. There's so many different spots.
Okay. 90% confidence interval. Do inverse t and make sure you can get the same value out with 14 n minus 2 degrees of freedom, n minus 2 degrees of freedom. You're going to do inverse t.
Oh, so we don't have to write any equation?
You're going to write an equation, but it's going to be an easy equation. It's going to have a lot of decimals, but the equation is going to be easy.
So we don't have to write all of this stuff. We can just do the equation, degrees of freedom, and
You can say degrees of freedom is 14. You can say t is this. And then here's the formula. This is the slope of the line. This is standard error, which I can get from the table. You have the table out in front of you. Back here. Here's the standard error part for the slope. That's what goes in for standard error. On the calculator, if you're using your list 1 and list 2, instead, last thing on the calculator, stat, over to tests, all the way at the bottom. Linear regression t interval. Remember, we're doing a 90% confidence interval, so that's an interval. Data's in list 1 and list 2. Confidence level is 0.9. Regression equation, alpha trace. It's in Y1. And there's the confidence interval. It tells you degrees of freedom is 14. There's the confidence interval. So again, almost all the way at the bottom, linear regression t-test. We are 90% confident that the actual slope of the regression line lies between these two values.